As you kind of ramp up and you grow that much, you'll start becoming cognizant of your cost, right? Because especially if you're doing it on the cloud, they provide a lot of sharp knives, and as you kind of play with them, you can cut yourself and bleed yourself to death in terms of money.
You're listening to Gradient Descent, a show where we learn about making machine learning models work in the real world. I'm your host, Lukas Bewald. Anantha Kancherla is VP of Engineering at Lyft, where he heads up the Level 5 software team working on building the self-driving car. Prior to Lyft, he spent time at Dropbox building products that help teams to collaborate. And before that, he worked at Facebook building mobile software at scale, delivering core experiences like Newsfeed on mobile phones. I'm super excited to talk to him. I was thinking it's kind of cool the way I assume that the goal is to make level 5 automation then?
Level 5 automation. Yes,
Automated driving.
that is our aspiration. But I'll take level 4.
I was wondering how you I don't think I've ever been part of a team with such a sort of like huge singular technical ambition. Like I was wondering how you kind of break that problem down to constituent parts, like how you think about what the
Yeah.
like weekly KPI should be when you have this gigantic goal.
No, honestly, like this feels for me like how I've always worked. I don't know why, because I guess like I started my career at Windows,
Uh-huh.
and it was like a few. By the time I left, it was like well into tens of thousands of people working, and so all working towards one product, singular focus on one product, right? So
Yeah.
it's this is obviously way smaller than what Windows was, but it's the same idea. And so now it's a good question, like what does it mean and how does it break down?
Yeah.
So usually in a project like this, you're going to have so many different skill sets. So ML is just one of them. Usually when people think about self-driving cars, like they mostly think about like the AI part of it. But the way we kind of think about it is that you're going to have, so first of all, you have to kind of think about the work that we do as in two parts. The work that happens in the cloud, the work that happens in the car, right? The code that runs in the car and code that runs in the cloud. And the code that runs in the car, you can think about it as, if you really want to simplify it, like it's kind of two parts or maybe three parts. So at the lowest level, you have the operating system. So again, if you want to compare it with like say traditional development environment, like imagine you have your OS that you're targeting, and on top of that OS, there will be a runtime that you're going to write. If it's Android, it's like Java or whatever, right? So there'll be an equivalent runtime that you want. And then on top of that runtime, you'll have your applications, right? That's how you would write a typical one. So it's a similar idea here. So you have your OS that is running on the car hardware. Now the car hardware is way more complicated than anything that like you've seen on the phones or PCs. It itself, we say it's like a data center on wheels. So there's typically a car has a lot of computers in it, but the ones that some of them we write software for, some of them are like come with the car, and they're all on a gigantic network. So you run so the most of the code that we write runs on what we call high performance compute. But again, different companies do different things. Like so, they will all, maybe they will factor the workload in different ways. So like you can imagine multiple smaller computers or one large computer and one small computer. There's different configurations possible, and you just have to figure out how you're going to break down your workload. And then on each of those computers, like you're going to run like a fairly, depending on how big it is, like you're going to run a fairly beefy operating system, or possibly even like no operating system if it is like a microcontroller.
Oh, I see.
And then sometimes like there'll be embedded processors, and then you'll run a very very thin microkernel. And then on top of that, we have like a framework that we build that's basically enables components that are the software components that are running on that one computer to work with each other. A good equivalent of that is in the open source world, you would have run into something called ROS. So it's very similar to that. And then, but you can imagine they can also communicate across the computers on the network. And then on top of that, you write your the functionality that actually makes it autonomous. But then you can imagine like that's just one, but you could also have a calibration functionality. There's a bunch of other little pieces of functionality that you would write. But the autonomous itself kind of breaks down into your classical robotics paradigm, right? Sense, plan, and act. So sensing is basically what in our world we call it perception. Then you have a block of code that predicts how the world is going to change. And there's a block of code that basically figures out where I am within the world. Within the world, it's called localization. Then there's another block of code. Once it knows, okay, this is what the world looks like, this is where I am at, and this is how the world is going to change in the next few seconds. How am I going to act? And what's the plan? And then it sends it down to the actuators, and that's the control part of it. So all of those, so those are all the kind of components that work on the car. And now there's a lot of code that actually runs on the cloud, um, for development reasons, as well as like even during deployment, like you do. So there are teams that actually build the infrastructure, because even though we are part of Lyft, and Lyft is like a very much a cloud company, the kind of workloads that the ride sharing part of Lyft does is very different than the kind of workloads that we run.
Right.
So the amount of data that we collect, or the amount of compute that we need, is very, very at a different scale, and requirements tend to be very different. So we have teams that actually think about what's the data, the data part of that infrastructure, and there are teams that think about the compute part of the infrastructure, and then we also have to think about testing all of these. So testing, obviously, you cannot unit tests. You'll do whatever with your code, but then there's also the other side of the testing, which is like on the road. You build everything and deploy it, but then there's a whole lot of other testing that needs to happen in between. So simulation is one example, where you try to run the software that you built, that you will eventually deploy on your car, somewhere in the cloud. And then we also have rigs that we build. These are called, we call them test beds, but another term that you will often hear is hardware in the loop testing. So you build, depending on which team it is, like you'll like embedded team will build their own like smaller versions of hardware. Then there will be full system tests. So there are different types of these test beds that we build, and you can think of them as like mini data centers that we have, and you run the code on those as well. So we treat them as if it's like another cloud. Um, and so we have teams that do all of that, and then there's teams that work on simulation. So all of these things eventually come together. In the end of the day, like it all gets packaged up into software that is deployed on in the car, and then we test that car on the road, and then those metrics are used to drive work on the software that runs on the car. But quite often it can also impact stuff that happens in the cloud. Like, for example, if you change your sensor and you capture a lot more data per hour, that means you may have to potentially replan like your storage capacity.
Right.
So things like that.
So I mean, I
I
guess
don't know. Did I answer your question there?
well, I have so many more questions actually.
Yeah. Go for it.
I'm thinking like, I guess you're at the point where you sort of have, you probably have some metric like how long you can drive without intervention that you're trying to optimize for, or something like that. Um, and then, but then do you like break it down by teams of like, we need to make our like perception 10% better,
Yeah.
or something like that? Or how do you think about that?
Yeah. So each team has, so it kind of breaks down, right? Like, so there's a top level metric for the overall system performance. And then
And
you
do I
can
have
do a
that
couple
right?
of
Is
things.
it like time between intervention, or is that the right metric to?
So California DMV reporting, that's what they look at. Like, so they look at it's called MPI, miles per intervention. So
Uh-huh.
how many miles do you drive before you have an intervention? So that's a very common metric that people track.
Uh-huh.
But then there are so many other metrics that you have to think about. Like, end-to-end latency is one example. How long does it take from, say, the time your camera captured a frame till the time that you reacted to it? So
I
that's one
see. Yeah.
example.
Right.
So you have to think of, there's a number of other metrics that matter. But of course, you can argue that all of them come down into an intervention, like some human had to intervene.
Uh-huh.
So that's kind of how, like, generally the industry is standardized around today. But, it's very controversial, because what is an intervention? How do you report it? All of that
Yeah.
is like, it's up for debate. But then we internally we track a number of other like broader system level metrics, and you can do two things. One is like you can apportion. Let's say you do MPI, right? The miles per intervention. You could apportion MPI to different components and say like, hey, was the the reason the intervention happened because we misperceived? Was the reason the intervention happened because our map was wrong? You can
Right.
kind of apportion those.
Uh-huh.
So, and then they kind of go down as far as they can go down. That's it, right? But then really that's just only part of the problem. So each metric, each component will also have its own separate metric. Like, so perception, for example, they may want to track like the precision and recall of seeing different agents. What's the precision and recall for seeing, say, a pedestrian or a car or a bus? And then you can further like subdivide that. Like, how good is my precision slash recall at 50 meters, at 100 meters, at like 500 meters? So you kind of have to. So there's lots and lots of metrics that eventually break down at the component level. That it comes down to at every component.
And how do you allocate your resources? Like, is the perception team a lot bigger than the planning team, or like what's the like roughly like where does
That's
stuff
a
go?
very good question. I'd say like they are most roughly similar between the two teams, but I don't think that there's a perfect science in terms of how you want to allocate it. You kind of have to look at the stage of the project you are in and the maturity, because sometimes each project, each part of the stack will will move at different paces, like
Mm.
depending upon what they're building. So let's say you're doing something which is highly machine learning dependent. So first you have to, I'm talking about like when you're starting from scratch, like in steady state, like of course it's very different. When you're starting from scratch, like when you're beginning, you first will may have to spend quite a bit of time like building your machine learning infrastructure, data gathering, all of that. So those teams you probably want to like populate first
Mhm.
before you start throwing models at it. And maybe you can get away with like a relatively rudimentary team,
Mhm.
a smaller team like of just a few core experts in the perception part. And then once that kind of is ready, then you start putting more people on that area, and maybe you don't have to like work so hard, throw additional people on the infrastructure side of things.
Mhm.
And once it's only like once you start like unlocking the ability to see the world, then you can start doing more and more complicated maneuvers in planning.
Mhm.
And then you start like pushing more into the planning world. So, and then you'll start hitting bottlenecks on that side, and then you'll kind of say, oh yeah, shit, I need to like add a few more people to unlock this thing in another area. So it kind of is very, very dynamic. So I wouldn't say like there's like a one standard formula through which we do resource allocation here.
I see. But is it sort of like where you're seeing the most like actually interventions being caused by, or is it like sort of where you see
Ah,
the most
uh,
opportunity for improvement?
I think interventions in a steady state world, like let's say there are a lot of bugs, ignore interventions. I mean, if you just like replace
Mhm.
interventions with bugs, it's the same problem in any software. Like, where do you have your biggest bugs, right?
Uh-huh.
And sometimes throwing more people at the problem is the right answer, and
Uh-huh.
sometimes it is not the right answer. In fact, it's the wrong answer. So you may want to like figure out putting the right people into that. Maybe you don't have the right expertise.
Mhm.
So it's not always clear that the resource allocation goes uh, is directly proportional to the number of bugs that you have.
I see. That makes sense. And like at this moment, is there a particular part of the chain that feels like the most challenging for you? That feels like there's the most room to improve?
I think that all like if you look at like the state of understanding and state of research in this space,
Uh huh.
uh, the place where there is a lot of scope for improvement is in the area of prediction and say behavior planning.
Mm.
So this is an area where like there's still a lot of active development going on. The industry is like changing fast. Just recently, I saw a really cool paper from Waymo's research team. So there's like a lots of activity going on in that world. So I would say that's the area which is developing quite a bit.
So this is like predicting where like another car is going to go, or like a pedestrian is
Yeah,
going
another
to.
agent. What will happen in the world in the over the next few seconds? Who should I pay attention to? What should I watch out for? All the things that as a human we take it for granted.
Right.
So those kind of problems.
So
Um,
so like inside of the car, the when it's operating right now, like how many different models are running approximately?
oh boy, I'm not sure I can tell you the actual number, but in terms of ML, like we have so many different ways of deploying these models, right? Like so, there's the on the car you deploy them, and
Uh-huh.
then in the cloud, like you have a couple of different ways of deploying them. And if you look at Lyft at large, like we have you can including rideshare. There's so many different ways. Like there are times when some teams at Lyft like will just run that model on their desktop once in a while,
Right.
pretty ad hoc. There are online the online loops that are running, like active learning loops.
Uh-huh.
Then there are like online learning that is happening.
Uh-huh.
Then there is they're all running in the cloud, right? Then there are models that run on a phone.
Uh-huh.
Then there are models that run in the car. So we have models like pretty much everywhere.
But I guess you're responsible for the ones that run in the car and the cloud for
Yeah,
maps,
and we
right?
also help the rideshare team as well. So there's a few people on our team like who help because we have a lot of pretty amazing machine learning people. So we also help the core part of it. So we do have visibility into like how they do it also. So in fact, sometimes our teams work on the cell phone models
Oh, that's cool.
or like the offline models. Yeah.
Wow, it's cool to talk to someone that's working on so many models at the same time. I'm really curious about like your infrastructure for all this. Like how often do these models update? Are they like is it like
It all
daily?
depends. It completely depends on which one you're talking about.
Right,
Um,
right.
say if you're doing the mapping ones, that's really dependent upon like the why you're using the model. Like so, sometimes like these models are used to help the operators. Like
Uh-huh.
if like as they work on the new techniques, new UI techniques or whatever, like where there's some additional assist they're providing, they may
Uh-huh.
update it when that time comes. Otherwise, like generally they work, it's okay because they're assisting humans as opposed to uh, doing
I
it on
see.
their own. So those models don't update as frequently, but the models that are operating on the car, you do that depending upon like the depending upon like what you're addressing and like which area that you're trying to improve. So
Right.
let's say like you're working in say winter, and
Uh-huh.
you see a lot of vapor or smoke much more visible. So there'll be like some parts of the code that are more impacted by all of that. So you'll see those iterating quite fast. In general, though, like these models tend to get like uh, trained and iterated upon on almost a continuous basis, like the ones which go on the car.
And I guess like one thing that I remember being kind of an issue, like do these models feed into each other? Like I remember like
Yeah.
when I was building models, like there's a big versioning problem of like one changes and the downstream ones need to update. Like do you actually like then retrain everything downstream from a model if you change like an upstream model? How do you keep track of that?
So okay, so the models do feed into each other, so that does happen. So this is where I would say that since I'm not day to day involved in this work, like I don't know the specific details about how the team manages it, but
Uh-huh.
the way they do that is I don't think that you have to go and retrain the downstream models.
Uh-huh.
The way we think about it is that you will have your model metrics, right? So you'll train your model, you'll get like a bunch of metrics around that model, but that's not enough. Like so, you have to kind of look at downstream metrics also.
I
So
see.
because quite often those tend to be the trickiest bugs also. Like so you'll kind of train your model and it all looks good in terms of the metrics and it's all working fine. You deploy it in the car and then you'll see like the behavior change quite a bit.
Right.
I don't know, like the car may decide to brake more often or it may, I don't know, do something different. And then you have to kind of debug that because the model's behavior has impacted something downstream. So then you have to kind of debug that. You don't. It's not necessary that you have to retrain those downstream models. Like you may just like want to go and figure out where the interaction is happening.
I
But
see.
there are a few things you do have to be very careful about. Like the validation set that you use to validate this model, and the training set that you do use for the model downstream. You have to be very careful of keeping them all separated, and hopefully there's no overlap. Otherwise, like you may introduce some weird artifacts. So those things like the team has to be very careful about.
Is it do you think it's harder with these kinds of like this modeling stuff? A lot of people have talked about that like predicting timelines is much more difficult. Have you found that to be the case or
The predicting timelines?
timelines of like improvements? Like I feel like software is already hard, right?
Yeah.
But with the models, it almost seems like it might be unknowable to know like how like how we get like X% improvement. Like, do you give your team goals where you'll say like, look, I want to see like a 10% improvement on this, you know, this accuracy metric, or
That's
does that
how
actually
they,
work?
they, they set themselves goals for improving it. I think ultimately, like, it's the same with any software. Like, so you set yourself a goal, but just because it's machine learning doesn't mean that it's a new problem.
Uh-huh.
The problem has got to do with the fact that you really don't know the perfect solution,
Right.
and you can't like really estimate what it'll take for you to get to that perfect solution. So the way you do that is by series of experiments, like by iteration.
Uh-huh.
Um, because if you know exactly what to write, then why will you can pretty accurately estimate the time. And
Sure.
sometimes that's the case. Like in say, like like, oh yeah, I need to I don't know, refactor this code. So you know roughly how long it will take, and you have test cases around. You can test it, so you know like all your unknown unknowns, all of those things are taken care of.
Yeah.
So you become more and more predictable over time. That's basically what I'm trying to say. Basically, what happens is that as you keep working on the problem, you start having a better idea about how long it will take because you started developing intuition about that particular area. So like then you probably have unit tests or like integration tests or some other tests that help you guide and focus on the right areas and uh, carve out the noise. So then you tend to kind of get a lot more uh, predictable in the work that you do. Then after that, like if you change your model, you come in with a new model. You know how many experiments you need to run, like like how to scan. I mean, then at that point it's like throwing money at the problem. You parallelize it and you you do a lot more work, but you are getting more and more predictable over time just because like you've built all this intuition and all this collateral to test. So I would say that going back to your question, are they predictable? Definitely not at the outset. But as they start working on it, they get better and better, more accurate about it in terms of how much they can.
And this is even like predicting improvements, like incremental improvements, because it gets more
I
accurate.
would say more like, let's say they're trying to fix issues.
Oh, I see.
Because yeah, so then they tend to get like more and more predictable about that. Now if they're bringing in, if they say like, oh, they set themselves a goal as saying I'm going to improve it by X percentage improvement. So the best way they can do that is by running a whole bunch of experiments and see like how fast they can come. So even that, like if your infrastructure is better and you have good set of tests and all that, you can get incrementally better. But I don't think that it's any different than any other software development that you can get super predictable with
Well,
model
I guess like
development.
one question or one thing that some people say is different, or that I imagine is different, is that like like when you think about like testing these models before you put them into production, do you test them against like a set of unit tests where it's like I insist that the model does this or that the car does this in this situation, or is it more like an overall accuracy of like I want it to kind of make the right decision 99% of the time? Like how do you think about that? Because aren't
So
these models
you
somewhat inherently unpredictable, or they're not always going to do exactly the same thing, right?
right. So you have to. Okay, so the way it works is that like you have a model and you will have a certain. I'm talking about perception models because like
Sure.
different. If you are doing something else downstream in some other area and planning, it's very different.
Okay.
The You will have a certain metrics that you reached today.
Hmm.
Okay, and then what you do is obviously you're working to go beyond that metric,
Hmm.
right? So you can identify that as like as a part of your model development. Like you
Hmm.
develop it, you have the model results, but that's not enough. So you then have to do like some level of integration testing.
Hmm.
You put it all together, and then you see like, hey, how's the downstream metric? Let's say if it's perception, so
Hmm.
the output of perception that like really planning would consume is like what we call tracks. So these are basically objects over time that
Uh-huh.
you track over time. So you have to get those tracking metrics improved or better or impacted in one way or another
Uh-huh.
in those areas. And then when you put that in the car, then like the top level metrics that you have, like how is the car behaving, like in whether it is driving, is it comfortable, is it safe? So
Uh-huh.
what are the metrics that you track for any of those things? So you have to kind of get that right. So you kind of have to like go through this entire journey. Like, so it's not like one, uh, you just tune the model once and then it works.
And are you able to like run these tests like every time there's a new model, or do you kind of like try to pass the first test and then sort of expand out?
Yeah, you have to run through the entire gamut if you do something brand new.
Have you seen? Do you have any interesting like examples of something that sort of improved the local test but made the more end-to-end
Yeah. I
test
mean,
worse?
there's a bunch of examples. The thing is, I don't know what I can tell you.
Fair enough.
Uh, yeah, yeah. I mean, there are all these cases like where you'll see the interaction between the model, say the upstream model, say in the perception, and what happens on the planning side. Um, I mean, I can tell you as a friend, but maybe I
Sure,
shouldn't put
sure.
it up there
Okay, no,
on the
no
cliff.
worries.
Like I was just giving you the example of that one where we had I was telling about, like in winter, like you have a lot more smoke that you
Mhm.
have to deal with. So we could see that like the model performance was pretty good, but like when we integrated it, it didn't work right. And so then we had to go back and see there was some interaction going on between like the upstream model and the downstream model that caused this problem. So we have to debug these. These kind of things happen all the time.
Uh-huh.
So the team over time has become much more rigorous about all these things. So anytime that they do this, there's a lot of automation built in. They test all of these things, and they yeah. So they have to go through the whole thing.
I see. It's like when you see teams improve models, is it typically that they've like collected more different data or kind of changed the data pipeline or like improved the model itself? Like, do you have a sense of like what's or I guess like
A lot
what's
of time, most often you'll see like the improvements happen with the right data.
interesting the
It's
right
less the
data?
model architecture. Yeah, it's less often that the model architecture itself has to be changed.
Got it.
Yeah.
But is it like an ML team itself that's like asking for different types of data sets? Like, do they kind of control that process, or is there like a data
So,
team?
no, we don't. Okay, so this is another big thing that we've been, I would say, somewhat religious about at level 5.
Uh-huh.
We don't have a notion of like engineering team and a science team or a data team.
Mm.
We just have a perception team. So I think like I'll tell you my mental model around like ML. I think ML is a skill. Um, so it's like anything, you know how to write Python, great, or you know how to write C++, that's a skill. So ML is a skill, but a skill alone is not enough. Like, so
Mm.
you need domain expertise. So just because you know how to write Python may be good enough for some things, but if you're trying to build, I don't know, some complex insurance thing, like you probably need to understand insurance.
Mm-hmm.
How do you divide the domain knowledge from the skill? In
Mm-hmm.
some cases you can, like, and you see that happening, like, so you'll have PMs write a spec and then they'll give you something and say like, go implement it.
Right.
But more often you'll see that like the engineer has to like really ramp up and truly understand like what the actual problem is, because if they have to debug something and they have to kind of really understand what is going on. It's the same thing in ML.
Mm-hmm.
So we've tried to kind of have a team that is called a prediction team. So their job is to predict. So we don't have a difference between like some data scientist or a data team and like an engineer. So it's the same people who have the domain expertise and have ML skills. And that's kind of how we've been operating so far.
Oh, that's cool. So all of your teams sort of have a mix of skill
Yeah.
sets.
Yeah. So I've seen this like this seems to be a pretty big debate in the industry. Like, there'll be this, oh, should we have a science and an engineering team
Mm-hmm.
idea? So the mental model I come up with is like, job of a science is to develop knowledge, the art, what they produce.
Mm-hmm.
Their production is knowledge. And
Mm-hmm.
the job of an engineering team is an artifact. In most cases, we are actually building an artifact. We are building a product. So in
Mm-hmm.
which case, I kind of see that science versus engineering divide to be less germane in these areas. You can have a research team. Their job is to produce knowledge,
Mm-hmm.
and that's okay. But when it comes to like developing a product, I've always found that it is better to have the domain knowledge and the skill people together. And ideally, if you can find the unicorns which have both, that's awesome. So, but
Right.
you'll have very few of those. But then you kind of have to like bracket them with people with the right skills. Does
That
that
makes
make
sense.
sense?
No, totally. Yeah. I mean,
Yeah.
we see the same thing with a lot of the companies we work with, and I think if I was in charge, I think I
Hmm.
would lean the same way as you. Of make sure that um, make sure that people doing ML are right inside the teams that are actually trying to accomplish something.
Right. And now coming back to the data question that you asked.
Yeah.
So if you are a domain specialist,
Hmm.
right, you already have a very good intuition about what is the right data that you want.
Hmm.
So and like we just said, like most of the problems seem to be about finding the right data
Hmm.
than the right model. So you have this like nice property where the team just knows like what is the right data to seek.
Got it. That makes sense. Is it challenging for you to deploy models into production? Like I've never had to deploy into hardware. Like is that a challenging step for you? Like do you find sometimes the model doesn't perform the same way you expected when it's actually inside the hardware, or
I
are you
think the
so?
biggest difference between what is say like when you're building it for like a cloud service versus what we are doing here
Mhm.
is is that the model they may be like a transform after training, right?
Mhm.
Generally, and the transform after training, you could say quantization or something like that.
Right.
So you have to have develop a good understanding about that, about the impact of that on
Mhm.
the model. The other thing that becomes really important, like when you're deploying it, and this is no different for mobile apps also, where you deploy models on your mobile phone,
Mhm.
is that like you have to be really careful about power and latency.
Mhm.
So you have to like really be rigorous about your op count, how much time does it take. So all of that you have to think about.
Have you built infrastructure to actually monitor these models as they
Yes.
run in production?
Yeah. Yeah. So actually, we have an internal framework that, in fact, I was just watching their video just before this. They were doing a demo because they had just built a new one, and
Uh-huh.
that takes care of all of these for you. Like, so it'll kind of like do the stats and everything, like when you are building and training your model and running your experiments. And in fact, we dump all of that probably in your tool.
Cool. Do you
Yeah.
do you look for some people talk to us about like worrying about feature drift? Like would you notice if like a sensor broke or something? Like if the model's getting a different kind of data, is that something you look for? Or is it mainly just like latency of the model?
Oh, I see. So you're talking about like the model, some strange behavior that.
Yeah, if it gets in like a weird situation where it seems to be struggling.
Yeah, so there could be so many problems, right? Like, so it could
Yeah, I'm
be,
sure.
yeah. So it could be some sensor has gone bad. Uh, I was just thinking about something specific here. Um, yeah, those things happen. But like the way we find out a bunch of these things is that increasingly, like we depend on something we call unsupervised metrics. So,
Hmm.
like imagine, like, what's a rough size of a bicycle,
Hmm. Yeah, I don't know
right?
what, like a meter or 2 meters
Oh no, it's going to be. I mean, width probably, but like
width. Yeah.
length probably a lot more than that than a meter.
Oh, oh yeah, I guess you're right.
Um,
Maybe a 3 or
yeah,
4. Yeah.
right. So, but if you see like a 50-meter bicycle, then you probably there's probably something wrong with it, right? So I'm
Right.
just
Right.
giving that as a very extreme example, but you can imagine that there's a lot of such heuristics that you could put together and
Hmm.
track. And if you start seeing like weird things happening out of that, that enables you to catch like lots of crazy bugs. And sometimes that's a really good way of catching long tail issues as well, because it may not result in a disengagement,
Right.
but you may see some weird behavior, or it may trigger a disengagement, but it is probably not often enough that like you know that that's a problem,
Right.
important
Right. Right.
problem to focus on. So we increasingly we depend on all these like unsupervised metrics where the data comes in, then you compute all these various interesting statistics, and then you figure out what is actually going on, and then you go back and debug it.
So well, it's so interesting. That's funny. I was just looking at Jira tickets, for my company, and
Mhm.
I was like, if you see like one thing wrong, does that like warrant a Jira ticket? Like, if you see one bicycle that's too big, will you actually like file a ticket against that, or how do you?
Yeah,
Um,
you should. You should. I mean, all of these things should be like filed in a ticket, and if it is that glaringly obvious,
uh huh.
then yeah, and you have the time to do it, to take a look at it, you will.
It'll
So
be like
it's
literally
always
one
a,
example where this thing is
yeah, yeah.
wrong. We're gonna ticket it.
So yeah, and again, this has got nothing to do with self-driving cars. I mean, we used to have similar problems in Windows. Like there'll be some weird one-off thing that you saw,
Yeah.
and we would record it. And then next thing you know, like if it's some code changes, that suddenly things tends to pop up, and then you're like, oh yeah, I've seen it in these environments and these situations, and then you kind of go and like track it. So I think
Right.
it's
Right. Right.
important to, anytime you see something anomalous, you just file it, and hopefully like you have more context that you capture, and then it'll help you debug.
And do you have a team that's tasked with looking for that, or is that like kind of everybody's looking for those things?
So we have a team that like obviously a lot of our reports come from the drivers driving the road,
Uh
but
huh.
then we also have to have additional people to go back and like look at the data and see if there's something weird going on. They're not necessarily engineers; we call them operations.
Uh huh.
So they kind of scan and like take a look at these things.
I see.
And of course, like engineers also like run into these uh, interesting cases, and they may actually look at it as well. But there's so much data coming in that which one do you look at, like, and how do you prioritize? That really becomes a more interesting problem.
Yeah, it sounds incredibly challenging. With
Yeah, yeah. I
yeah.
mean, by the way, this is a problem of like any software that has scale, right? So in our case, like I mean, I've had again like the luck to work on uh, major products that operated at scale, and it's the same problem. Like whether you're running like newsfeed at Facebook, or like you're running like some issues in Windows, or like you're running a car on the road for thousands of miles.
Yeah.
So then you'll get like lots and lots of reports, and that's the issue of diversity. And
Yeah, I guess
then
these
you
are
still
just
have to
issues of sort
prioritize.
of complexity and scale.
Yeah, it's a complexity and scale problem, right? Like, so if it's an extremely simple problem, you have a sanitized test track and you're running your car in that, then yeah,
Right.
it's like probably you can be very selective about what you do and be very rigorous. But when you're running it on the road, anything can happen.
Right.
And it's kind of like, you run like your operating system on any kind of PC anybody built, and you still have to figure out what's happening.
And so you've I guess you've been at Lyft for 3 years almost now.
Yeah.
And the organization must have grown quite a bit in that time. I'm kind of curious
Oh, yeah.
how processes have just changed as the organization has grown and things have solidified.
A lot, right? Like, so it's kind of interesting. There are teams which were non-existent, and then they've kind of been built, and then now they're at scale. Like, I mean, I would say the current perception team is one of those, like, which is now operating at scale. But then there are still some new teams that are forming, and it almost feels like they're doing things which were, say, a perception team or some other team was doing it at their beginning. So, but of course, they have a lot more guidance now because there are other teams that have path broken for them, and they get through it. A few things happen. One is like as you kind of get like more um, bigger scale as the organization has grown. In the beginning, we would not care about like where the training was happening. Like
Mhm.
the engineer would train it on their desktop, the workstation that they had. It would be like that. Like as the team started growing and more engineers started coming in, and reproducibility and all of that started becoming a real problem because multiple people are working on the same thing. So
Mhm.
then you start becoming much more rigorous in your process,
Mhm.
and that's fine. That'll work only like if you have maybe like a four of them working together. But then once you grow beyond that, like process won't fix it, or like mutual agreements won't fix it. So you probably should be building a framework to help
Mhm.
you standardize that process and like just make you not worry about all the moving parts. So that's why, and then after that, you'll find that like that framework doesn't last you, and
Mhm.
then you'll write a new framework for the new scale of problems that you run into. And we've gone
Mhm.
through all of that. Then another thing that will happen is like as you kind of ramp up and you grow that much, you'll start becoming cognizant of your cost, right? Because especially if you're doing it on the cloud, they provide a lot of sharp knives, and as you kind of play with them, you can cut yourself and bleed yourself to death in terms of money. And so again, like you start becoming very very careful about, and you kind of try to build your ML frameworks or whatever. Maybe it's not just ML, but even
Mhm.
simulation. You start building your frameworks to help keep that in check. Then you start becoming very very rigorous about your data partitioning, and you have to have versioning, and you track all of them in like a in a tool, and you probably want a custom tool, which is kind of why how we ended up like building our own analytics tool internally to track a number of these things. And then you start getting even more like to track all your experiment data, and then we built in weights and biases. Then you start like running into time problems. You do more and more complicated models, and then you want to get done with your experiments faster, and then you start getting into distributed training. And we've gone through this entire journey. I'm sure there's more.
Yeah, what's next? What's
Yeah, I'm sure there's more. I'm sure if I talk to somebody at Google, they've probably gone like even further than a lot of the things you've done.
Well, thanks. That was well said. We always close with two questions. I'm kind of curious how you're going to
Mhm.
answer these. So one is like, it's machine learning specific, but maybe you could expand it to autonomous vehicles. And I guess what's one underrated aspect of machine learning or AVs that you think people should pay more attention to than they do?
I've noticed that there's a tendency to think of it as just as a skill, and it's like you throw data at it, and then you train, and it gets better, and you can do that over and over again, and then you may be able to get a good result. But I always go back to the idea that like one very underrated aspect of machine learning is that like it has to be coupled with domain knowledge. You really have to like have a good understanding about like what problem you're solving, and have a good understanding of the domain. In fact, I would say spend quite a bit of time like really understanding the data that you're going to get. And then, because I said, right, the right data is more important than like a lot of data. You actually, there was this interesting case for us, like where we made some change, and we cut down our data usage by half. It became way cheaper for us to even like, and the model became more accurate.
Mm.
So, so that's what you get by like actually genuinely understanding. And I think I would say, I don't hear too much about this no, the domain knowledge. So I
Mhm.
think that's something that I would say is uh, very important in this area, uh, especially with machine learning. But you could argue it's true for anything. But
Yeah, yeah.
yeah,
um, all right, well said. All right, so here's our last question is, and you've actually deployed several serious machine learning products at scale. And just what's been like the biggest challenge in getting taking them from kind of the experimental stage to actually running in production?
so one of the biggest problems with machine learning is that to getting it to generalize, right? So there are lots of long tail events, and the data is typically very sparse in your data set. And trying to figure out why that happened, what that happened, is generally really difficult. Um, so this is one area where I think uh, you have to figure out how to combine machine learning with other techniques uh, in a place where you want to uh, have absolute guarantees in a system like a robot, like where there is actually no human intervention. In other areas, I think there's some very nice properties if you're doing like a human assist. So ML has a very nice property of being able to do good enough, and let's say you get like some 99 point some number of nines, and then the remaining can be like augmented by human intelligence. But if you really are trying to do a perfect build a robot where it has to be completely autonomous, you have to figure out like additional ways in which you can have some guarantees,
Mhm.
and that's actually quite challenging, figuring out everything.
Seems challenging.
Yeah.
Yeah. Awesome. Thank you so much. It was a real pleasure to talk to you.